Hi everyone, welcome back to Chem Story. Today we're looking at one of the most important reactions of alkynes, hydroboration oxidation. This reaction gives us a really clean and efficient way to turn alkynes into carbonyl compounds. What makes this reaction even better is that the mechanism is not only simple, it's also highly selective. By the end of this lesson, you'll see exactly how it works, what products you get, and why it follows anti-Markovnikov selectivity. Alright, let's jump in. Let's start with a quick overview. When a terminal alkyne reacts with an organoboron reagent, like R2BH, it adds across the triple bond. This happens through syn addition, where the boron and hydrogen add to the same side of the molecule. That gives us a boron-containing intermediate, which basically sets up everything that follows. Later on, during the oxidation step, the boron gets replaced by an OH group. But here's the important part. The position of the OH group is already determined in the addition step, because that's where the boron went in the first place. And since boron prefers to add to the less substituted carbon, the OH group ends up there too, following anti-Markovnikov selectivity. We'll walk through the full mechanism soon, but for now, just keep this in mind. Hydroboration oxidation gives you aldehydes from terminal alkynes, and it does so with excellent regioselectivity, all thanks to how the boron adds at the start. Now let's break down how this reaction actually works, step by step. In step 1, the terminal alkyne reacts with an organoboron reagent. This addition happens in a syn fashion, meaning the boron and the hydrogen both add to the same side of the triple bond. As a result, we end up with a boron-containing intermediate, and that sets the stage for the next part of the reaction. In step 2, we bring in H2O2 and OH-. That kicks off the oxidation step. Here, the boron group gets swapped out for an OH group, and that gives us an enol, a compound with a double bond and an alcohol on the same molecule. Again, look at the regiochemistry. The OH ends up on the less substituted carbon. That's a perfect example of anti-Markovnikov addition at work. In step 3, the enol doesn't stick around for long. It quickly rearranges through tautomerization, and that's what gives us the final carbonyl compound. If the starting alkyne was terminal, you'll end up with an aldehyde. If it was internal, you'll get a ketone instead. So this last step completes the reaction, turning that enol into a stable, functional product. Let's zoom in and walk through what's really happening step by step. We start with a terminal alkyne. That means the carbon at the end is triple bonded to another carbon, and it still has a hydrogen attached. When we add the dialkyl borane, both the Br2 and the H add across the triple bond at the same time in a syn fashion. So the Br2 and the H end up on the same face of the molecule. That gives us what's called a vinyl borane intermediate. Next, we move into the oxidation step. We add hydrogen peroxide under basic conditions. The hydroxide ion deprotonates the hydrogen peroxide, turning it into a hydroperoxide anion. That anion then attacks the boron, forming a new bond between the oxygen and the boron. From there, we go through a couple of rearrangements. Eventually, the boron is replaced entirely by an oxygen atom, and we're left with an enol. But the enol isn't stable. It quickly rearranges through tautomerization. The electrons on the OH group shift over, the double bond moves, and we end up with a carbonyl compound. So overall, this is a smooth and efficient transformation, taking a triple bond and converting it into a carbonyl group, with full control over where the oxygen ends up. Now let's finish up by looking at the regioselectivity and what kinds of products you can expect from this reaction. If you start with a symmetric internal alkyne, both ends are identical, so after hydroboration oxidation, there's only one possible outcome. You get a single ketone. But if the alkyne is asymmetric, meaning the two ends are different, things change. Now the enol can form in two different ways, and that leads to a mixture of two isomeric ketones. And here's the cleanest case, when you use a terminal alkyne. In this situation, the reaction gives you just one predictable product, an aldehyde. The OH group always ends up on the less substituted carbon, perfectly following anti-Markovnikov selectivity. So if you're looking for a clear-cut, no-complication transformation, this reaction is a great choice. Alright, that wraps up our deep dive into the hydroboration oxidation of alkynes. We broke down the full mechanism, talked about the regiochemistry, and saw how this method gives you predictable carbonyl products, whether it's an aldehyde or a ketone, all based on the type of alkyne you start with. Thanks so much for watching, and as always, I'll see you in the next Chem Story video.